Hello, everyone. Welcome to the MIPAR 2.0 update webinar. My name is John Sosa. I am the CEO and co-founder here at MIPAR Software. Thank you all very much for joining us and giving us an hour of your morning or afternoon, wherever you may be joining us from. We've got some exciting things to show you today. Joining me will be Pavel Sewell. He is our Senior Applications Specialist. And also in the room, we have Jacob Newton and Lawrence Small from our team, who will be fielding questions as they come in. Feel free to type in questions at any time. Those that they feel they can answer on the spot, they will do. And any that we'd like to save until our QA sessions, we will do so. We'll have two Q&A sessions, one after the first case study presentation, the next at the end of the webinar. And we'll do our best to get to everyone's questions. If there are some that we just can't, you're always welcome to contact us by email at support@mipar.us or go to our website at mipar.us. We have a live chat service. So thanks again, everyone, for attending. Again, my name is John Sosa. I'm the CEO here at MIPAR. And what we're going to be showing you today are not only a demonstration of some of the new features that are in our largest release today, 2.0, things like simple recipe mode, a recent recipe library, and more consolidated reporting. But more importantly, we're going to be showing you those features in the frame of two exciting case studies that we have partnered with collaborators on that have not only saved our partners enormous amounts of time, but let them reach realms in their image analysis that they were previously unable to. So to get started, I want to introduce the two case studies that we're going to be speaking about. There'll be a material science case as well as a life science case. I'll present the materials. Pavel will present the life science. And after a summary of each, we'll launch into a live demo, taking you through the story of these two cases. On the material side, we partnered with our valuable users at NASA. We're very grateful for their partnership on this case. And this case will cover some novel and objective particle analysis in the widely used aerospace nickel-based superalloy. This particular case will demonstrate a fully automated workflow that not only addressed many of the challenges that NASA and the entire superalloy community have been facing for almost 6 decades, but it will also demonstrate, for one of the first times, image analysis quantification of this microstructure that was validated by what's known as a phase extraction measurement technique that is historically much slower, much more time-consuming, much more expensive, but more trusted than image analysis. So for one of the first times, that more traditional phase analysis approach validated the image analysis, which, as you can imagine, is orders of magnitude faster and more visual than the traditional approach. So we're very excited about this case, and we're thrilled to be able to give you a brief overview of its story today. The life science case will then be presented again by Pavel, and he is going to go into a supervised workflow demonstration in MIPAR that has successfully addressed a very common yet very challenging application in life science, which is muscle fiber quantification, that historically has been left often to manual drawing of lines within each fiber because a fully automated or even semi-automated workflow just never wound up being more efficient. So he's going to demonstrate this supervised workflow and how it has saved our collaborators at Nationwide Children's Hospital orders of magnitude in time, improved their accuracy, and very importantly, reduced user bias in the measurements. So we're going to begin with the NASA story. I did my PhD in material science at Ohio State University, and I can tell you firsthand how many challenges there are in the material science community around image analysis, both in many different aerospace alloys. I did my thesis on titanium microstructure characterization, and that really led to the development of MIPAR in the first place. We needed a tool as users that could handle these challenging cases and give us efficient and unbiased results. So what you'll find unique about our team is that we are all end users of the product. We all have a passion in this product because we built it and we use it to solve real problems. So I was around the nickel-based superalloy problem set for quite some time during my studies, and I can tell you this is a very exciting development that we've put together with NASA, having such confidence in these volume fraction and particle size measurements, having them validated by other techniques. That has been a sought after solution for quite some time. I think in the paper that you see down here, our folks at NASA referenced 6 decades as this problem being in the making, begging for an automated and objective solution. So NASA came to us because they had come up with a novel low kV secondary electron imaging technique that gave them much more confidence in where these particle boundaries lay. It didn't require any etching, which if you're around this problem, you know how significant that is. There was no confusion, at least from a human standpoint, about where the particles were. So that checked a big box. But it wasn't the easiest problem image analysis wise. These particles are not decidedly darker than the background, although they might look like it. You've got these very refined precipitates here, this smaller size scale in the center. And it was not something that traditional thresholding or other more commonly used algorithms could tackle. So they engaged with us with this problem, and our team in under a day was able to put together this solution for them using the very same version of MIPAR that all of our users have access to. This particular customer was just one that wanted to rely on our expertise to build these algorithms, or recipes as we call them, quickly. We sent this over to them and they were able to begin using it same day. They deployed it at scale to their hundreds of images using our batch processor, and they were able to accomplish their goals rather quickly. And importantly, as you'll see, there was objectivity in where these boundaries were defined. It wasn't left up to someone with a slider deciding where to stop the boundaries of the particles. So that's my introduction to the NASA study, and now I'm going to jump into a live demo of MIPAR here to take you through this story here. So here we have MIPAR open. These are our 5 applications that come. The 3D toolbox comes as part of our 3D extension. The image processor is probably where you'll find yourself spending the most of the time. It's where recipes are built and run on single images. The batch processor you'll see in action, where you can take a recipe and apply it to hundreds or thousands with just a few drags. And the post processor here, you'll also see this is our batch review, our batch quality assurance environment, where you can actually see the results of your bulk image processing before you make the all-important measurements. So to open an image in MIPAR, it's very simple. You just drag one in. Here is one of the gamma prime images that we worked with NASA on. And to load the recipe that we have created, you can use our new recents menu here in next to the load recipe button. It remembers the last several recipes that you've loaded in, so it really becomes your personal integrated recipe library, where with just 2 clicks, you're running now this algorithm. So you see it running through the various stages down here. And when it's done, not only will it present to you the detection results, but you also get a report of all of the measurements that have been baked into the recipe. This is just simple volume fraction measurement here, so-called global measurements, things that result in one image or one measurement per feature type. You'll see we can build on this report and make it as comprehensive as we'd like and still have it baked into the recipe executable with one drag. So what you'll see here on the right now is our simple recipe mode. This is a rather advanced recipe, despite the short time it took to build. It is that lengthy because it had to address many of these image analysis challenges. However, in simple mode, you see which you see with this lock switch engaged, all you see are the few flagged settings that we have identified as the critical ones that you might need to adjust should you apply this to another problem. So you're still able to get under the hood completely by sliding this lock switch and customize the recipe infinitely. Our image analysis experts enjoy using this tool to build algorithms rapidly from the ground up. But with simple mode now, the majority of our users see a very clean, simplified presentation of the key knobs that you might need to turn on this, named in friendly non-image analysis jargon ways. You can hide layers, of course. So the red here are our refined precipitates. The green here are the coarser ones. And that size threshold is something that, of course, can be exposed to your users if you want them to play with that. We actually looked at the histogram of all particle sizes in order to decide on what that threshold should be. So as you know, if you're with image analysis, there's a lot of iteration that goes on with building these algorithms. And MIPAR provides a non-destructive auto-recorded algorithm builder that lets you do what-if scenarios and go back and try new things without having to spend time writing macro code or erasing your last bit of work to go back to a previous state or struggling with multiple windows. It's all right here for you, and the effort that you put in is just on solving your problem, not using the software. So you'll see we also have another layer here that I've added where we've ignored edge features, and we'll use this when we make feature measurements. And the only things I want to hit on here are, this knob here controls the detection strength of the secondary particles. And this is really this is using an edge find approach that is rather agnostic to overall intensity changes, image to image. That was one of the challenges that they struggled with well, there were four really. One, they needed to handle brightness variations image to image. You can notice that here's one image, and here's another image. It's slightly lighter, slightly less contrast. There were even some gradients in some images. So they had to have an algorithm that worked in the presence of gradients and overall contrast variations. So there are pre-processing steps in the recipe that get rid of gradients. This edge find approach is rather agnostic to overall intensity changes. And we then use some marking tools that we're happy to go into details of if you're interested in, things that look at contrast on a relative to the image scale and can look at just find sort of the darkest patches in the image relative to itself, and then keep what's inside the edge found boundaries as particles. So a combination of those marking and edge find tools let us tackle this challenging problem where, despite what your eye might think, the interior and exterior of the particles are roughly the same gray value. So that's really what this controls. Here we have a minimum size setting for what counts as a secondary that can change the difference between green and red. And what you would see is if you updated this, you would see the classification change before you real time. So that is another element of how that goes into how quickly you can adjust this algorithm and customize it for your needs. Make a change, hit accept, the rest of the algorithm rebuilds, and you see an updated classification. Then the tertiaries here, finding these fine particles was challenging for any product, but But our local thresholding allowed these very subtle local intensity differences to be picked up on and properly identified the particles as such. Again, we have a minimum size cutoff here for the tertiaries. And what I then want to hit on are these two optimization steps, because as anyone who's been around image analysis knows, just because you're using a computer, it doesn't take away the subjectivity of it. You could add a growth step that grows the particles by a pixel or two, and you'd still be hard pressed to decide exactly where to draw this boundary. Do I bump it out a pixel? Do I shrink it by one? There's always a gradient, as you can see at this high zoom level. So where do you stop? Well, where you stop affects what you measure. If you bump them out a pixel, you're going to measure a higher volume fraction. It wouldn't be fair to always play with your image analysis parameters to give you the volume fraction you hope you measure. We'd like to be a little more objective in how we decide where to draw these boundaries. So what we've come up with is an engine called optimization that can be applied to, I think, roughly 10 different steps in a recipe. The ones that are optimizable are listed in our user manual. And how it works is, what this step really does is it tries to shrink the particles. We've renamed it optimize secondaries, so it's clear what the purpose is. But what you'll see is if we run this optimization, and this is something that happens automatically every time you run the recipe, so it's flexible and dynamic image to image, but let's see what it looks like. So if we edit the optimization, all these settings can stay, and we say I want to try shrinking the particles from a strength of nothing up to a strength of 5 with half steps. And what you're going to see now is the software try to shrink the particles, and at each shrink, it's measuring what's the match quality between what I've selected and what's in the original image. And then at the end, it presents to you a plot of match quality versus shrinkage strength. And it's chosen the one for you that maximizes the match quality. So now you at least have some math behind drawing the boundaries where you have a auditable and defendable reason for your volume fraction measurement. And again, this is something that repeats on every image. So if there are changes in image to image that need accommodation, this can often accommodate them. Maybe the next image, for whatever reason, the imaging conditions were different and needed to use a depth of 2. It's going to choose 2, but it's going to choose 2 based on this same mathematical criteria. And you see then we've done the same things on the tertiaries. We've shrunk them iteratively from 0 to 5. And it comes back and says, nope, they were good as they were. They don't need any shrinkage. They're already the best match they can be. So that's optimization, and that was really key in coming up with this solution. Because the recipe produced objective measurements, and then those measurements were validated by another approach, that gave NASA great confidence that this algorithm paired with their imaging technique can likely become the new standard for gamma prime quantification. I believe we list that paper on our site. It's also searchable. You also have the link provided in the slide I showed, and if any of you would like a link to the paper afterwards, just let us know. We can post it in the chat window even. We're very happy to get that to you. So once you have the recipe built, as we did for NASA, we delivered this to them and they began using it same day. Now comes the reason you did this in the first place, which is measurements. So as you saw when the recipe loaded, you can measure simple things like area fraction of all of the layers. These are now, as part of our 2.0 release, completely customizable, and you can assign them to any of the layers or only some of the layers that you have active with this Choose Layers tool. So we've programmed the area fraction measure to only run on these two. We're going to save this layer, the fully contained particles, for other size and shape and proximity analysis. So let's go ahead and take a look at some feature measurements and build this report out a bit. If we have, let's say we want to go and look at proximity and size and even shape-based analysis on a per feature basis. We'll go up to our measure features, and we're going to run these on the no edge secondaries. So we have a number of metrics with descriptions next to each of them, categorized by different types. A link here will take you right to the page in the user manual, and you can get further discussion on these measurements as well as reference papers for some of them. And for size, I'm going to look at the caliper diameter. That's one way of measuring size, is the longest line that fits inside of the object. We could also look for proximity at average neighbor distance, which was of interest to NASA. This is a way of looking at particle spacing, and as a new metric that was added in 2.0. And then let's also take a look at eccentricity, which is somewhat of a normalized aspect ratio. You'll see me add these to the report in a second, but first I just want to visualize them, which is something that we and our users enjoy doing in MIPAR. Oftentimes a spreadsheet can't tell the whole story. This is great for some things, but you can often miss trends in your data. Even if you plotted this on a histogram, you don't see necessarily where these measurements came from in your image. And yeah, you could label everything with a 1 through however many features are in here, 205, but it's not very much fun to give someone an image with things labeled with a box in their center, 1 to 205, and a corresponding spreadsheet. What you'd rather see is something like this, where you now have every feature immediately colored by its size. There's linkages between the data and the image. Click on a feature, that cell highlights in the image. Click on a cell, that feature highlights in the image. So there's very nice explorative connectivity between those two areas of the tool. You also have the corresponding histogram of particle size, color-coded the same way as it is on the image. You can even drop a line on the histogram where this feature sits on it. You've got your stats down here, the mean size, the min, the max, the standard deviation. So here we have things colored by size. We can quickly color by spacing, and we see these lighter blue ones in the interior are closer spaced to their neighbors on average, or I'm sorry, the darker blue are closer spaced, and the lighter blue are a little bit further spaced. And then these yellow ones are somewhat of an outlier, likely because they're towards the edge of the image, but in this field that was captured, this is the average spacing here visualized. You can also add, other criteria to the recipe. Maybe you don't want to keep ones as close to the edge of the image. That's all very customizable and doable. Take a look at shape, and now we have particles colored by aspect ratio, normalized from 0 to 1, 0 being a perfect circle, 1 being a straight line. All this can be exported and saved to put into your report. So this is our color by measure feature. Now, to finish up in this tool, let's say we go back into here and we say I want to measure the same things, caliper diameter, eccentricity, and average neighbor. You can choose what stats we want to measure from each of those in our final report. We add that to the recipe. And now when we run this whole report here, we're going to get the area fraction of those two layers, and then the mean feature measurements of this layer. So again, in one drag, you could have all of this done for your team. So before we move into the life science section, I just want to hit on the batch processing capabilities, because NASA didn't just need this run on one image. And even though it's pretty simple to run this on other images, if you have more than 5 or 10, you're going to be looking at batch processing. If you wanted to run this on another image right inside of the image processor, you could simply just drag in another image and say reload I'm not going to save my changes that I just made. And that's going to open the image, rerun the algorithm for you, and produce the same results on the next image. So if you've got between 5 and 10 images, some users just choose to quote unquote batch process this way, drag in an image, click a button, get your next image results. But if you've got more than 10, you're probably going to want a batch processing workflow. So right from the image processor, we can say launch batch processor. That's going to bring in the recipe for you. Done. And now we're just going to take the images that we want to batch and say go. This takes roughly 1 minute for these 3 images, maybe less. And in the interest of time, I've already got the post-processor environment up. Once this was done, you would hit view results and it would open the batch in the review environment. So in here with a slider, you can flip through all images that were part of your batch and evaluate how the algorithm worked. You've got manual editing, Photoshop type tools down here to correct any mistakes quickly, save and move on to the next. So it's a very accelerated supervision environment. And once you've evaluated your analysis in batch and are happy with it, then we can generate the same kind of report that we made on a single image basis, but on all images at the same time. So that might look something like, let's measure the area fraction again. And we'll go set up some feature measurements now. And again, combining feature measurements with this list of globals into one comprehensive report is a big step that we've taken in 2.0. Let's check off the caliper diameter and the average neighbor distance. We'll say add to report. And then when you click generate, just choose what you want to measure on what. We'll measure the area fraction on those two and the feature measurements on the fully contained secondaries. Click accept, and now all 3 images are going to be measured as you've requested. When we get area fractions, mean particle size, mean particle spacing. Copy this and paste it into a report or save it directly into an Excel sheet. And there you have it. So that was a quick run through on the solution that we put together for NASA in about a day's time. And we're very pleased with the collaboration and the paper that they produced with us. And we're really looking forward to helping the rest of the SuperAlloy community adopt this as a new standard. So with that, I'm going to turn it over to Pavel, and he's going to take you through the life science case study.
John, did you want to answer some questions on this part of the webinar?
You are correct. Thank you very much, Pavel. I got ahead of myself. So we are going to open it up for a 5-minute Q&A session, and we'll do our best to address everyone's questions. If there are more than we can handle in 5 minutes, we do have another Q&A session at the end of the webinar. And of course, we're always available by email or live chat. So let me go ahead and review some of the questions that were brought up during the session here, and we'll get to those. Okay, looks like we have some nice questions that have come in. Thomas has asked if we can get an idea of the complexity of the recipe, and absolutely, Thomas. As you'll see, our product caters to both the sort of one-click, one-drag users that need recipes built for them, as well as image analysis experts that have come up through the ranks of Fiji and Python and are looking for an environment in which they can unleash their skills more interactively, more quickly, more non-destructively. And that's what you'll find with the recipe technology. So, of course, if we just click this lock switch here, you'll see the entire recipe here for you. So this was a 41-step recipe, which I would place on the moderate scale. Again, our team was able to build this in and vet it and clean it up and package it for our client in under a day or so. All of these steps are recorded automatically as you do them from the menu bars. All the image processing functions are recorded, and they're grouped by chapter. So they kind of give you an idea of what this section of steps do. So this is our noise reduction step. In here is some of the steps where we go about finding the background and normalizing some gradients. Then we go in here and we look for the secondary particles. Then we go down here and we try to remove some falsely identified particles and fill in unwanted holes. And you see these flag steps here. You simply click on a step and hit flag, and now it becomes part of what you see in simple mode. All steps also have notes available, which I should have mentioned earlier. And when you're in notes mode, you can type in custom tips for your users as to what this step does and what they might need to adjust. And those notes are available inside of simple mode too. Down here is where we optimize the boundaries. Here we remove edge secondaries to set up the secondaries layer. All of this, again, is built graphically with no coding at all. You click a step, it adds to the recipe. You can go all the way up to step 2 and make a change and hit accept, and the other 39 just repeat for you. You can remove a step at any point. You can insert another one. It's never intended. It's intended to get the software out of the expert's way and just let them solve the problem. And that's why we've been able to solve these problems as quickly as we have for as many of our clients as we have. So that's an insight to the recipe. Looks like they also have a question on cumulative size distribution for the nickel particles. That is, I may not be completely understanding the question. The cumulative size distribution is something that our users usually do in other plotting softwares once they have the histogram from MIPAR. We are working on adding additional plotting enhancement features to the software in the 2.0 series. Things like curve fitting and cumulative size plots within the histogram. But for now, what you can get here is just the histogram of the data. You can export this count versus bin data into a spreadsheet, and in probably under 30 seconds in Excel, make yourself a cumulative size distribution. Looks like we're also, we've got some users looking to measure area percentage of different phases or minerals in an image. As you saw when we ran the nickel or ran this particular recipe, once you have your segmentation done, which is always the challenging part and is where MIPAR excels, just add an area fraction step to your recipe right up here. If you didn't have this in here, you go to measure area fraction relative to the entire image. You then get an area fraction of all your layers. And then inside of here is where you can customize what you want that measurement to run on. If you just want it to run on the secondaries, then there you go. So area fractions, of course, no problem to run in MIPAR. And it looks like we've hit the 5-minute mark. So let me just touch real quickly. We had a question if there was any validation of the segmentation result. And yes, I wanted to let me re-mention how in NASA's paper they discuss how they took the results of our objective segmentation and they compared it to a phase extraction plus mass spectroscopy technique, basically wet chemistry. And for one of the first times, as they report in the image analysis, pursuit of this problem. The segmentation area fractions match nearly identically with the historic phase extraction wet chemistry technique, and that is why they are so confident in promoting this as a new standard. So thanks all for the questions. I'm now going to turn it over to Pavel for the life science section.
Hello, everyone. And I can see that there is still a lot of questions coming in. And for the sake of everybody's time, feel free to contact our support or schedule a call with us, and we can discuss this in further detail. We're happy to work with you and with your problems. Again, there's a pretty wide range of researchers here. So just, feel free to reach out, and then we can discuss this in more detail. So the application that I want to talk about today is kind of the muscle morphology characterization problem that's been around forever. This is a very popular assay where we take a muscle cross-section that's been fixed, stain it with H&E, and then use that information to kind of generate our average diameter measurement, and then classify the muscles based on how damaged they are or whether they've recovered. This is a fairly challenging problem that's been around for a very long time. This was how I was introduced to biomedical research, where the first month of my undergraduate research was spent measuring diameters of these muscle fibers. So this problem is a little bit kind of dear to me. And I'm going to talk a little bit more about why it's challenging. I'm going to show some examples. The most recent methods paper that I found for preparing these samples is listed there, and we'll provide these later on. The images that you're going to see today were from an evaluation from Nationwide Children's Hospital, from the Center of Gene Therapy. And let's go ahead and move forward with the demo. So if everybody can see my screen, let me go ahead and open some of these images, kind of describe what the real challenge is. And a lot of variation that we see here comes from, sample preparation, imaging technique, and then just the variation in the biomedical morphology of these cells. We see that there is examples of damaged fibers there. It's very hard to differentiate between the boundaries. It's very challenging to kind of tell where these fibers begin and end, even though it's not difficult for you to do this by with your eyes. When it comes to imaging software, this has been a challenge for a long time. The other example I want to demonstrate is an example like this, where these are fairly dense. There's no real contrast of the muscle fiber boundaries. So it poses a very strong challenge for software to be able to identify this. What the current method to do this, primarily doing this manually, where you would sit down and draw lines across these fibers to generate the size distribution and the mean size and so on, and then you would basically classify these fibers based on the location of the nucleus, which is what these dark features are. What I want to demonstrate today is a semi-automated solution where the software is capable of getting 90% of these fibers for you, And what you have to do is simply make some minor edits to some of these key steps, and it's able to regenerate the entirety of the recipe for you. So, for example, we can go in here, change this back to outline. We notice that there's a couple of fibers that were not perfectly selected. We're going to go ahead and fix that. So we don't have to be perfect with the segmentation. MIPAR is able to kind of clean this up for you after you're done. We know that this line is not correct. We can just fill this in and cross this line out. We don't have to worry about removing it entirely, and then simply hit accept. Once you accept, what you're going to see is in real time, the software rebuilds itself and it reclassifies and reseparates these fibers for you. The next step is simply making sure that the software had identified the internal nuclei accurately. And again, this is as simple as going through and kind of spot checking. And if I remember correctly, depending on whether or not I had my coffee that morning, I can do one of these entirely manually, where I'm measuring these in 5 to 10 minutes. And that was very painstaking type of work. This is much more streamlined, where I can simply look around, find a nucleus that was not identified, and then make the change. For this specific case, maybe there's one here. I can go ahead and circle to erase to make sure that there is anything that is being picked up. Again, I'm going to hit accept, and what you're going to find is in real time, the software reclassifies these fibers. I can then generate my measurement quickly. I can see the total counts of these fibers, and then from here move forward to generating either a caliper diameter or an equivalent diameter. Caliper diameter is simply the longest line through a feature. An equivalent diameter just assumes that your fiber is a perfect circle, and it generates your diameter from that. Once you have this data, again, as John demonstrated, it is very nice to be able to color this based on the measurement. You get your statistical information immediately in the bottom right corner. You can copy this into your report or your spreadsheet. You can export this directly into Excel and kind of move forward with the next image. And this takes, a fraction of the time than it would have to do this manually. And once you're done with your first image, go ahead and reload the recipe. Don't need to save the changes. On the next one, again, this does a very good job. It gets you most of the way there. You can look for spot checks where there's bad sectors, where stuff is not perfectly separated. And we can go ahead and do that fairly quickly. Things like this, I can go ahead and just hit fill freehand and just circle stuff like that. And what you're going to find is that MIPAR is capable of immediately cleaning that up for me, and it doesn't have to be perfect. So I can actually do this fairly quickly without having to worry about having a perfect segmentation, and MIPAR kind of does the rest of the work for me. Again, then same thing. Look for confirm that my internal nuclei is what the software found, and very simply go in, click to fill, hit accept, and move forward. I'm ignoring any of the fibers that are touching the boundary, mostly because they're not fully contained. They're not very representative of the actual size of the fiber. Again, same thing, regenerate measurement. You can copy this directly from MIPAR. You can then go ahead and generate your diameters. You can view them, or you can save them directly to a file if you don't need to visualize these like that. And these create very nice reports and representative figures for publication and presentations during kind of your lab meetings to give your team a very good idea of what you're working with. So again, this is just a workflow that we've put together fairly quickly, that is robust and saves you so much time and energy from having to manually be able to draw lines through these fibers. The other problem that I've found is that a lot of people they vary how they draw their diameter through a fiber. It's not always consistent and can result in kind of random error, which is not what you want when you're doing this type of work. But yeah, I think I kind of went pretty quickly here just for the sake of time, make sure I covered everything. But demonstrating here again in version 2.0 of MIPAR is this really simple recipe mode where we can view our layers very easily, be able to control this interface from the simple view, exposing just the key steps for us without having to really worry about the entirety of the algorithm. The algorithm itself is, I can probably show that some of you might be interested in, is around 44 steps long, not very complicated, pretty fundamental approaches such as color deconvolution, and then going in and separating this based on contrast. But I think that's pretty much it. I want to leave some more time for questions and for John to wrap this up. So I'm going to go ahead and hand this over back to him.
Thanks very much, Pavel. I will go ahead now and go back into our slide presentation. And what we'll do now is I'll move into some of the closing statements and then reserve, as long as anyone wants to stay afterwards, for the final Q&A session, where we can, both Pavel and I can work to address some of the questions we weren't able to get to in the chat window. So to finish up on summarizing the case studies, both NASA on the materials side and Nationwide Children's came to us with very real, very specific challenge sets involved in these two studies. On the NASA side, they struggled with brightness variations from image to image, contrast gradients across the image, very similar gray values between particle and background, tough distinguishing very refined fine particles that the eye can see, but basic thresholding really can't in the center between the big particles. And then most importantly, being objective in how we draw these outlines, not just deciding to draw the boundaries where the user felt comfortable stopping the shrinkage at. And with MIPAR, in a very short amount of time, our team was able to put together a solution to address those challenges. We sent the 7 kilobyte recipe over to their team and they began using it same day. As you saw, with a couple of clicks, you can apply that to hundreds or thousands and then actually see how it worked on all of them. And to our delight, the image analysis was validated by a phase extraction technique, which has often been the stumbling block for other imaging techniques and analysis algorithms. I do want to commend NASA on their low KV imaging technique. The specifics of it are referenced in the paper, and we'll be sure to include a link to that paper in the follow-up email from this webinar. I know it involved minimal to no etching, low KV electrons, and a scan rotation of 180 degrees and a frame averaging. And that really gave some of the best gamma prime images I've ever seen. And I have had some experience working with many in many different prep conditions. There's really there's very strong confidence in where the boundaries lie. Now we just needed the algorithm to find them reliably, and we were able to provide that. On the life science side, challenges included wild variations from sample to sample based on the health of the tissue and other imaging conditions and white balancing changes. Other things, artifacts in the image is that might have looked like nuclei or looked like small fibers. Again, there was a need for objectivity, and the workflow, even for semi-automated attempts, was still cumbersome. You know, we do our best at MIPAR to meet the need and the challenges of each and every one of our customers and provide solutions to your problem. So as try as we might to fully automate every solution, what we want to make sure doesn't happen is when the fully automated approach doesn't work, because sometimes it doesn't. The human brain is an amazing thing. We want to let you take it the rest of the way without making the entire solution worthless. So just having a one-click button that says find fibers without the ability to get in there and fix it if and when it will break on some cases is not what we want to offer. We want to offer accelerated, automated solutions are great when they work, but the semi-automated ones that don't severely compromise time savings are often where the real value can be. Their efficiency improved from, as Pavel mentioned, 10 minutes per image fully manual to a minute or less, with much less subjectivity and user-to-user variability. So to wrap up the closing statements, I just wanted to reiterate how we have seen firsthand how the MIPAR product can cater to two very different opposite ends of the spectrum users. If you're in the camp that doesn't really know much about image analysis, doesn't want to worry about the jargon, certainly doesn't want to worry about coding, you just need answers from your images. You just need numbers out of your pictures. MIPAR offers an environment where anybody with a keyboard and mouse can drag in recipes that are either from our freely available recipe store on our website or built custom quickly by our experts. Just drag them into the software, get your measurements, batch them if you want to, and move on to your next project. We offer training and consulting to your engineers, even on just how to run a recipe, not necessarily how to build one, but if you have some people in-house that want to build recipes from simple to hard problems, we offer accelerated training for that. I wanted to mention we're coming out with our MIPAR Academy. We'll release one course at a time. The first course will be the fundamentals of image analysis. It'll be a Udemy course that can be applicable to any software package, but will feature MIPAR for much of it. We're excited about this self-learning material, and we'll be sure to notify everyone when that's out. And then we also do job shop work. If you are one that doesn't even want to worry about software, you just want to send us images and get reports, we do have that service available. Then on the image analysis expert side, there are folks that have been hardcore ImageJ, Python, OpenCV users who have fallen in love with MIPAR's environment. It really is a creativity enhancer, where the sky is the limit with the algorithms that you can put together. You don't have to worry about debugging your code or managing your code or managing window names. As you are thinking and creating and experimenting and coming up with an algorithm, MIPAR is just listening to you and recording what you do, and you never have to worry about undoing any of your work. You make a change at any point, everything just updates. Before you know, you've made your algorithm and, by the way, recorded a macro at the same time without even realizing it. So our users are able to put together some pretty incredible solutions, ones that we never envisioned the software capable of without adding a single line of code or running a single plugin. We are growing as quickly as we are because while we do well with the simple problems, we have consistently been able to enable our users to reach image analysis, automate image analysis problems that other products couldn't get to. And that's where the real excitement happens. You saw the optimization engine to take out subjectivity and some of the key steps. You saw how you can build in reporting into the same recipe and deliver that to your users to run in one drag. And I wanted to mention that we are coming out with a beta version of an API for the first time. And this will be, first iteration will be a Python API. And it's going to let you take a recipe that you've cooked up in MIPAR and run it inside of your own applications with a single line of code. So we'll be announcing more of those details as the beta comes out. If you are interested in that, drop us a line. We're more than happy to get it into your hands. And this is something that our experts have been asking for a while. We're really excited to see what it can enable. And it really is to thank you for giving us your time. We are very appreciative of your interest in MIPAR, and we want to continue to work to get it into as many hands as we can. So that's all that I had for the closing statements. We're at 11 o'clock right now. We will stay as long as anyone would like to answer questions. Let me go ahead and take a look now in our record of questions that came up and see what we can address here. Pavel, I'm sorry, if you have any that you wanted to start with while I review, feel free to go ahead. Both he and I will be jumping in this last Q&A session.
Sure. There's a couple of good questions about kind of stitched images and how MIPAR handles them. We have already worked with a lot of research groups that do these mass image stitches and try to do analysis on just absolutely massive image data sets. And we kind of take it from case to case. We have successfully solved those problems. We can't say exactly whether it's or not it's going to work for you without you reaching out to us and us taking a look at the problem. So feel free to contact us and we'll be happy to work with you. A couple of notes about it. Once you start working with images that are 200 megabytes to a gigabyte in size, MIPAR will open and run its algorithms on an image of any size, but your computer hardware, your workstation hardware just has to match that. So, if you're working with large images, we do recommend that you have a workstation with hardware specifications that kind of match that workload. I think John can answer the question about the TEM images. I think you can answer that a little bit better than I can.
Yeah, certainly. MIPAR is completely agnostic to how the images are collected. If you take a look at our applications page or our recipe store, you'll even see satellite images that MIPAR has been used to analyze from Google Earth. So it's simply a set of pixels to the software, and it's all about coming up with an algorithm that teaches the computer how to recognize the features that you recognize as a human expert. So we have analyzed many TEM images. The format is not a problem to us. We open over 150 different formats, including proprietary ones from different microscope manufacturers. I know we have even gone down to the high resolution atom imaging, where some folks like to pick up on individual atoms and measure their spacing to nearby other ones or measure their HADF intensity. Certainly many of TEM applications are very doable in MIPAR. That's also maybe a good moment for me to mention that anyone is always welcome to send us a sample image for a recipe. If you go to our site at mipar.us/try-image, or just go up to the navigation bar under recipes and select Get Custom Recipe, we get hundreds of submissions from folks looking for a rapidly built custom solution that we can often turn around in sometimes a few minutes. That's really what we're about, is helping you solve your problem, not just providing stock solutions that are tough to fix when they break. So please feel free, if you're able, you're welcome to send us your particular problems. Pavel, was there anything else you wanted to address?
Not that I see. I'm still looking through these list of questions, and I think we covered most. I think there was a question on kind of the maximum pixel size of an image that we can open, and again, that's something that it has to depend on the hardware of every computer. So you have to just be able to load the images into memory and then be able to process them further. But it's not something we can say for sure until we see the exact scale of the images that you're working with. There's a question on can we open VK4 images from Keyence? John, do you know the answer to that?
I can take a quick look here. You go to our website also, MIPAR.us, and up in the support tab, you go to the user manual. That'll take you to our web-based user manual that is updated frequently. And there's, under the Getting Started section, there's a supported formats page with a link next to bioformats to the over 150 formats that we open. If you click that formats link, you're taken to a list of formats, and you can do a quick Control F in there to see if Keyence's file formats are supported. I'm not sure. There's a lot of formats to comb through. I don't see Keyence immediately, but I know from experience that there have been other formats from different manufacturers that we didn't think we could open that we could. So it is very, very possible. Worst case, I'm sure that your acquisition software has the ability to export in some more generic formats to get the image into MIPAR. So
there's one more question.
Yeah.
If there are 4 mineral phases and they're of different colors, how do you measure the area of individual minerals? The approach that I would take is a color deconvolution approach, where basically what you do is have the software break up the image into its color, its individual colors, not just red, blue, and green, but the colors of the minerals, and then do the segmentation from that instead of maybe the original color image or so on. And MIPAR has a very nice color deconvolution tool that lets you simply manually circle the different minerals, and it will generate a channel operation that is representative of that color. So basically that's the approach, the first approach I would take. This might be, or it might be some other, a simpler solution, depending if some of the minerals have, if they're a circular type of morphology, or if they have more of a rough shape, we can maybe separate them based on that as well. But I completely understand that it is fairly challenging once you get to, more than your 3 colors.
There is, we've also had success using our color cluster tool, where you simply input the number of colors that you're trying to discriminate. That's literally the only step. And the software will then use a k-means clustering algorithm in RGB color space, and without any other parameters, objectively determine where the boundaries between those 4 colors lie and split up the image for you into your 4 classes. That's been a repeatable and objective solution that we found to some of these color segmentation problems. But like Paul said, all solutions all problems are different. Many of them can be solved a number of different ways. MIPAR is about enabling the users to solve the problems that they need solved as quickly as they can, and for enabling then the others to have those solutions delivered to them easily if they don't have the experience to make them themselves.
So it looks like there was a cutout during my last answer. and I have to apologize for that. Yeah, like I said, just the color deconvolution tool can be of great assistance to when it comes to kind of separating features based on their color and so on. Because basically what it does, it converts the color images into a grayscale representation of that specific color instead of just separating the image into its red, blue, and green.
Mm-hmm. Yeah, the channel operations can be quite powerful, and when we introduced the color deconvolution, it was really fun to use because it's a form of machine learning in a way where you know that there's some orange somewhere in the image, and it can be a struggle to come up with the right linear combination of red, green, and blue to brighten up the orange and dim everything else. With the color deconvolution, you just circle the orange, and it spits out the optimum channel operation. It might be something like 0.17 red minus 0.8 blue plus 0.3 green, and then your orange is lit up, and it's a simple thresholding problem to find the orange. So that definitely could be a powerful solution for the mineral quantification.
I think there is a question about pricing. It's kind of hard to say the exact price of how much it's going to cost for your group. It honestly varies on whether you're doing commercial research or academic research, the size of your group, and so on. Feel free to reach out and schedule maybe a quote call. That way we can price something out that's right for you and kind of work with you based on your funding situation.
Well, I'm looking through the question list, and I hope we've been able to address everyone's questions. You will be receiving a follow-up email from us after the webinar that will include a published recording of the session that you're welcome to rewatch and scrub through at your leisure. We'll also be sure to include the link to the NASA paper if you'd like to take a look at it, as well as probably a few other points, a reminder about the webinar 5% promotion. And we're always here. We have a team that works tirelessly to cater to your needs and build solutions for you. So reach out to us anytime by email, chat, or phone, and we'd be more than happy to speak with you. If Pavel doesn't have anything else, then we can close out this webinar and look forward to the next one.
No, I think you got everything. And yeah, again, thank you everybody for attending, and we'll look forward to working with you.